to introduce our speaker today, Professor Xiaolan Wu. She is Enrico Fermi Professor of Physics and Vilas Professor at the University of Wisconsin-Madison in the USA. Xiaolan has had a long and distinguished career in high-energy physics, being involved in the discovery of the J-psi particle, which was the first evidence of the charm quark back in 1974. She had a leading role in the gluon discovery in 79 and has been very active all this period and contributing in a decisive manner to our understanding of nature by the discovery of these particles. She was also involved in the famous discovery of the Higgs boson observation in 2012, and she continues very active and is now exploring how quantum computation, quantum machine learning could contribute to high energy physics. So it's a great pleasure and privilege to have you, Xiaolan. Thank you very much for being available for our Quantep seminar, and the floor is yours. Thank you very much.
Thank you, Yasa. It's a pleasure to give this seminar. Okay, so I'm, as you all know, can you hear me well? Yeah.
Yes.
Can I have the screen back? Yeah, okay. So can I go back to slide number 1? Somehow this is not working.
So let's see, is Chen who is sharing the screen, am I right?
Yeah, yeah.
Okay. So I think we got the slides now, and
but
Chen,
I need slide 1. Yeah, okay, good.
Excellent.
So my topic today is application of quantum machine learning to high energy physics analysis at LC. And we'll be using quantum computer simulators and quantum computer hardware. Well, I'm new in this field since only about 2 years, and also part-time. And because the other part is high energy physics in Atlas. And I have assembled an international and interdisciplinary team of high energy physicists and quantum computing scientists. We are from physics department and computer science department of University of Wisconsin-Madison. And we have colleagues from our collaborator from CERN Quantum Technology Initiative. They belong to the IT department at CERN. And we also have collaborators in IBM Research Zurich and IBM T.J. Watson Research Center. We have scientists from Quantum Institute Fermilab and scientists from Computational Science Initiative, Brookhaven National Laboratory. We also have a CNN Institute from State University of New York at Stony Brook. And finally, we have collaborators from quantum computing and AI research, Amazon Web Services. The next one. So we started simply about, just mentioned, machine learning for high energy physics. One of the major objectives of the experimental physics at LC is to discover new physics. Machine learning, the simple definition is application of artificial intelligence that provides systems the ability to automatically learn and improve from experience without being explicitly programmed. Machine learning has become one of the most popular and powerful techniques and tools for high-energy physics data analysis. It greatly enhances our ability to identify rare signals against immense backgrounds, which is what happened in LHC environments. So it's very important for discovery of new physics. However, there are a number of issues, but I just list two of them. So heavy CPU is needed to train complex models, and the training time increases with more data. It may also lead to local optimization instead of global optimization. So the classical machine learning algorithm commonly used in high-energy physics data analysis are these three: boosted decision tree, an algorithm that incrementally build and assemble decision trees and combine all the decision tree to form a strong classifier. And the second one is support vector machine. It maps the input vectors into a high dimensional feature space through some nonlinear mapping. In this space, an optimal separating hyperplane is constructed to separate signal and background. And the third one we use a lot is called neural network. It's a computing system made out of a number of simple, highly interconnected processing elements, which process the information by the response to external inputs. So I don't need to say anything about quantum computing, but quantum machine learning is the intersection between machine learning and quantum computing, obviously. It may lead to more powerful solution and offer computational speed up, which is the most important point, by exploiting the exponential large quantum state space through the action of superposition, entanglement, and so on. Quantum machine learning could possibly become a very valuable alternative to classical machine learning for high-energy data analysis. So let me just tell you what our goals are. We want to perform LHC high-energy physics analysis with quantum machine learning to explore and to demonstrate that the potential of quantum computers can be a new computational paradigm for big data analysis in high-energy physics. And this will serve as a proof of principle. This means our work is trying to make a proof of principle. Our present program is to employ the following three quantum machine learning methods. Number one is variational quantum classifier method. Number two, quantum support vector machine kernel method. Number three, quantum neural network method. We apply those methods to LHC physics, LHC high-energy physics analysis, especially, for example, TTH, Higgs production in association with a pair of top quarks, and also Higgs to 2 muon. These are the two LHC flagships analysis. So we study quantum machine learning method on gate-based quantum computer simulators and hardware. And we collaborate with 3 different companies. One, IBM quantum computer simulators and hardware using IBM Qiskit libraries. Number 2, Google quantum computer simulators using Google Cirq and TensorFlow quantum libraries. And the third one is Amazon quantum computer simulator using Amazon Braket Cloud Service. Here's a picture from an artist, and in the center, you can see the red box, and that's the Google quantum processor. Next. So we have applied quantum machine learning to the 2 LHC flagship analyses, as I mentioned before. The first one is Higgs production in association with 2 top quarks. And another one is Higgs to muon pairs. So just briefly tell you, in the classical analysis at LHC, the TTH, where Higgs decay into 2 gamma, the observation of the TTH production, as I mentioned, Higgs boson production in association with top quark pair, by Atlas and CMS at LHC, directly confirmed the interaction between the Higgs boson and the top quark. And top quark is the heaviest known fundamental particle. So on the right, you see a mass peak. So if you identify in the event the topology of 2 top quark, and then you look for the 2 photon mass peak, you will see the peak, which I show in this plot, the red one, which is a fitted result. And this is the peak of the Higgs boson. So in this analysis, Atlas used boosted decision tree. So as I mentioned earlier, it's a classical machine learning technique using the HE-boost package. The Atlas collaboration observed this TTH Higgs to gamma-gamma process. And so is CMS collaboration. Our study performed the event classification of the TTH analysis with Delphis. What is Delphis? Delphis is a simulation sample, and we use this sample and we use quantum machine learning. Next. So for the second flagship analysis, H2 at LHC, although the coupling between Higgs boson and the 3rd generation of fermion have been observed, currently the coupling between Higgs boson and the 2nd generation fermions is under intensive investigation. Higgs to mu is the most promising process to observe such a coupling by Atlas and CMS at LHC. Again, for Atlas, we use the boosted decision tree, BDT, and Atlas collaboration intensively search for the Higgs to mu decay. So in particular, our study performed event classification with the channel called VBF, which you have 2 jet and the Higgs decay to muon pair, using again the Delphis simulation sample and using quantum machine learning technique. So just a word about Delphis simulation. Delphis, this package has been published and is a program that performs fast simulation of multi-purpose detector response. It reconstructs physics objects for physics analysis, including photon, electron, muon, jet, and missing transverse momentum. In principle, we can use our collaboration Atlas simulation or Atlas data, but at the start, we use Delphis simulation to demonstrate our feasibility of studies. Next. So let me just go through our workflow with quantum machine learning. So on the left, you see we have input events. For example, for TTH Higgs to gamma gamma, the number of variables we use is 23. And then you go to the next step called PCA, Principal Components Analysis Method. This method is to convert or combine the 23 variables or whatever number of variables into fewer variables to match the number of qubits. At this moment, we are still working in the way to be dictated by number of qubits. And then after PCA, we go to feature map. Feature map basically is encoding the classical variables to the quantum state. So currently in our study so far, the number of encoded variable has to be equal to the number of qubits. We have number of qubit 5, 10, or 20. And then after that, we will use the quantum machine learning, one of the three methods that I mentioned to you earlier. Next. So since I have three methods, so I divide the description into one at a time. The first method, we use variational quantum classifier. We use this for the TTH and Higgs to mu analysis. So this method, variational quantum classifier method, was introduced by IBM in 2018 and is published in Nature in 2019. So this variational quantum classifier method can be summarized by me in a very simple form in 4 steps. So this page is highly simplified. So you can see in the figure, there's a pink box. So we apply feature map in this pink box circuits to encode the input data into a quantum states. The next one, you can see an orange box. So we apply the quantum variational circuits, which is W theta, which is parameterized by gate angle theta. And number 3 is those bunch of green boxes. We measure the qubit state in the standard basis, so-called standard basis, and you can see for 1 qubit and 2 qubits, etc. And the last one is we assign the label called signal or background or probability or signal or background to the event through the action of diagonal operator. So next, sorry, I haven't finished. So during the training phase, a set of events are used to train the circuit W theta to reproduce the correct classification. Then we use the optimized W theta and then to apply to the independent set of events. So we will have an independent set of event, not the same set that is used for training. And the independent set will be used for evaluation and another set for testing, so we don't bias ourselves. Next one. So in this method, we use 10 qubits. So by using 10 qubits, we successfully finished training and testing 100 events with the IBM Qiskit QASM simulator. That's the name of the simulator. When we say 100 event, means 100 event for training, 100 event for testing, and 100 event for variation. At the reason we're using 100 event as an example here, this was our earlier work. Right now we are successful using more events. So here we use the so-called Q simulator, which is provided by IBM called Qiskit simulator. This simulation incorporates the hardware noise. And then the quantum circuits are optimized to best fit the constraints imposed by the hardware. For example, the hardware we impose the qubit conductivity, hardware noise, and also the nature of our input data. Let me define something which is useful for the rest of the talk. This is a curve called ROC curve, ROC, receiver operating characteristic curve. And it is a graph that shows background rejection on the vertical axis and signal efficiency on the horizontal axis. So I will be plotting a lot of such ROC curve later. The area under ROC curve is called AUC. The AUC is used in machine learning a lot to quantify discrimination power of the machine learning algorithm. So you measure you determine the AUC for different algorithms. The next one. So now this, again, in our beginning research, we use this variational quantum classifier introduced by IBM for our 2 LHC flagship analysis. On the left is the result of the TTH process. On the right is Higgs go to mu process. So using the TTH analysis data set, we use only 100 event, 10 variable, because we make it simple that we do 10 qubits. And the same for Higgs mu. So in this plot on the left, the variational quantum classifier on the simulator, which is color blue, it performs similarly with the classical BDT, which is green, and the classical support vector machine, which is yellow. So for this simulation, we always simulate at least 10 data sets to avoid fluctuation. We average the 10 data sets. On the right-hand side, we do the same thing for Higgs to mu. Now, in the table, you can see For the AUC, the area under the ROC curve, the first line is the VQC, the vector. So the variational quantum classifier, which is the quantum machine learning. And the second line, which is in green, is BD, classical BDT. And the third line, SVM, is the classical machine learning method. So you can see that in this simple analysis, the quantum machine learning and the classical machine learning are not that far off. And next one. So now we are a bit ambitious besides doing simulation. We want to actually run in the IBM hardware for these two processes. With the help of our IBM research rig, the help of Fermilab and Brookhaven National Lab, we carry out a number of jobs on the IBM superconducting quantum computers. And one computer is called Bloomingen. It's a 20-qubit machine. Another machine is called Paris, a 27-qubit machine. But in each job, we only use 10 qubits of the quantum computer. And we use only 100 events for training, 100 events for testing. For each analysis, due to the current limitation on the hardware access time, we apply this variational quantum classifier method to only one data set, not like the simulation, we use 10 independent data sets. And believe me, to get access to hardware nowadays, well, it's very, very difficult because it's very expensive to run jobs in the quantum hardware. Next one. So this is a curve you may not understand, but it doesn't matter. The vertical scale is a function called loss function. The horizontal scale is called iterations. Iteration is indicate the number of times the algorithm parameters are updated for training. So we have 100, 200, and 250. So the important thing of this loss function, although the definition is written here, is to see if this curve, by the way, this curve is from hardware, which is most important. This curve decreases as more and more iteration is performed. That means the machine is able to do its job or distinguishing between signal and background. Next one. So here is the result of the hardware. So on the left figure is TTH Higgs to go to 2 gamma. On the right, the Higgs go to 2 muon. So the red curve is the IBM hardware, and the blue curve is the IBM simulation. So using TTH analysis of data set only 100 event and 10 variable, because these are run in 10 qubit machine. And also for Higgs muon to mu pair, again, a data set of 100 event, 10 variables on the 10 qubit machine. We run for 250 iterations. The result of this variational quantum classifier from the quantum hardware and the result from quantum simulation are in good agreement. And we were although these are very simple plots, but we were very excited when we first saw that the hardware and the simulation agree quite well. Next one. So now I'm going to go to the second method. The second method is called quantum support vector machine kernel. Again, to our two LHC flagship analysis. Next. So this method, I'm again really simplifies the explanation. So the quantum, the SVM kernel method is introduced by IBM again, published in the same Nature journal in 2019. So you map the classical data to a quantum state using quantum feature map function. And then you calculate the similarity between any two data events. And this similarity is called kernel entry. And using the quantum computer to determine this kernel entry. Then you use the kernel entry to find a separating hyperplane that separates signal from background. Next. So we are performing TTH and Higgs Tumble analysis using this kernel method with 10 qubits. So for the feature map, we do use a customized feature map. With this, we modify ourselves. The quantum feature map circuit encodes the classical data to a quantum state and contain tunable parameters. And then we go to grid search to optimize this kernel performance. So here is the results. So we are using the IBM Qiskit simulator, and the simulation represents the ideal quantum hardware that has no device noise. In this particular simulator we use, we did not include the hardware noise. So using TTH analysis dataset again with 100 events, but we also at time go on, we become more mature. We use 3,200 events. Again, using 10 qubits, that means 10 variable. This quantum SVM kernel method on the simulator, which is, you can see is the blue curve, it achieves better performance than the classical BDT, which is the green curve, and the classical SVM curve, which is yellow. And on the right, for the 3,200, you cannot see so well, but you can see better in the next figure. Next page. So here is the AUC. You remember the area under the ROC curve as a function of events. And you can see the blue curve, which is the quantum kernel, the quantum machine learning with the kernel method. And the green is the BDT and the yellow is SVM. So the yellow and the green are the classical machine learning method. So you can see here, although, what is encouraging is that it consistently higher AUC. The quantum curve is higher than the two classical curves. At this moment, the advantage of using this kernel method is that the running time for both simulator and hardware are shorter than the earlier method we were using. And so it enables for us to work with larger number of events instead of only 100 events. So using the TTH analysis data set, we have 100 events all the way to 3,200 events, 10 variable. The QSVM kernel on the simulator, which is blue, may have a quantum advantage over the classical BTT, which is green, and the classical SVM, which is yellow. So this is something we are all looking for, quantum advantage. So we are seeing a little bit hint of it, and so it gets us excited. So this curve average over 30 runs. Next. This is even more interesting. This is again the area under rock curve for TTH. And so it's plotted as a number of qubits. The number of events is always 3,200 events. So the QSVM kernel method also enables us to work with a large number of qubits. So using the TTH analysis and using a data set of 3,200 events, from 5 qubits to 15 qubits, we have observed or getting the hint of the kernel on the simulator, which is blue, may have a quantum advantage over the classical BTT, which is green, and the classical SVM, which is yellow. Next one. So that was for TTH. We were not as skillful in the Higgs to mu. So in this curve, you can see the blue curve, the green curve, and the yellow curve. The two classical and one quantum, they seem to be on top of each other. So at least they perform similar to each other. Next. However, we cannot resist our temptation to run those jobs with hardware. So again, we feel very lucky we can actually get access to the IBM hardware. So for this plot, which is TTH, we use the machine called Paris of IBM. It's a 27 qubit machine, but we use only 10 qubits for the TTH analysis. So the hardware, you can see the AUC is 0.85. The simulator of AUC is 0.84, which is extremely close. Due to the current limitation of access time on the IBM hardware, we only process one data set of 100 training events and 100 testing events. So using the TTH analysis, the QSVM kernel method on the quantum hardware, the results compared with the QSVM kernel on the quantum simulator, they are in good agreements, which make us very happy. Next. So again, not only TTH, we apply the same thing for Higgs to mu using applying the quantum machine learning with the IBM hardware called Paris. So the hardware AUC is 0.86 and the simulation is 0.84. So basically, the two results are in good agreements. Next. So now, not only we work with IBM, we also work with Amazon. So we apply this quantum SVM kernel method, our method 2, with the Amazon simulator for the TTH Higgs to mu mu and Higgs to gamma gamma analysis. The Amazon bracket quantum computing cloud service provides quantum computer simulators and quantum computer hardware. Our group has implemented the QSVM kernel algorithm using the Amazon bracket Python software development kit and the Amazon quantum computer simulator, and apply the algorithm to TTH analysis. The next bullet is more difficult. We are investigating the feasibility of running QSVM kernel algorithm on quantum computer hardware provided by Amazon bracket, which they have, including the Rigetti machine, which is based on superconducting circuits, and IonQ based on trapped ion. So far, we have not done so. The next one. So now, employing we have employed the quantum SVM kernel method with the Amazon simulator on the TTH Higgs to gamma gamma analysis. So you can see the shape of the ROC curve with 3,200 event 10 qubits, and they seem to be all on top of each other on the table on the right. So we listed the area under the ROC curve for TTH 3,200 events. So the top one, 0.886, is from IBM simulator. The next one, the purple one, 0.886 also is from the Amazon simulator. And the classical BDT is 0.879, and the classical, the support vector machine is 0.878. So now we can say, using the 100 to 3,200 event with 10 qubit or 10 variable, we train the classical BDT and train the classical SVM. The quantum kernel estimator with IBM and the quantum kernel estimation with Amazon are very similar. So we do expect Amazon performance and IBM are very close to each other, although the work to make them run are not identical. So in the next plot, again, using the quantum support vector machine kernel method with the Amazon simulator for TTH analysis, you can see the AUC as a function of events all the way to 3,200. So you actually the top one is the top curve is the blue and the purple together. The blue is IBM, purple is Amazon. They are on top of each other. And the yellow and the green, they are the classical machine learning method. So on both Amazon and IBM quantum simulator, the quantum kernel estimator method may have a quantum advantage over the classical SVM and the BDT for the TTH analysis data sets. Next one. So now I go to method 3. We employ the quantum neural network for TTH analysis. Next. So quantum neural network is combining neural network algorithm and quantum computing together. Many QNN quantum neural network models have been recently studied in the field of quantum machine learning. For example, Google used the TensorFlow quantum library and IBM using the Qiskit library. Next. So this, again, a very simplified picture and have been developed by our group in using the quantum machine learning algorithm. So the first layer is a classical layer. We transform the input data so that the number of output matches the number of qubits. The second layer is the core layer, is a quantum layer that encodes classical data into quantum states. And again, we use the variational circuit containing tunable parameters to measure the quantum states. And the last layer is a classical layer, just convert the measurement of the qubit into classification label, the probability of being a signal or background. The 3 layers are trained together to maximize the overall performance. Next. So we employ this hybrid quantum neural network method for TTH. We use the Google Quantum Computer Simulator. It's called Google Cirq and TensorFlow quantum libraries. And we use the IBM Quantum Computer Simulator and hardware using IBM Qiskit libraries. Next. So here's a curve, which is a 5-qubit hardware curve, which we apply the QNN, the quantum neural network, on the IBM hardware, which is called SX. That's the name of the hardware. And you can see in this rock curve, the blue one is the simulation, and the red one is the hardware. So the AUC for the simulation is 0.2822 and the hardware is 0.01. So the performance of the hardware is not as good, but this is only for one run. It depends on the hardware status at the time. One day it may have more noise than another one. Next. So then we have what we are plotting here. On the left-hand side is the raw curve from TTH, 800 event, 10 qubit. On the right, 3,200 events, 10 qubits. And the area under the raw curve is listed here. So for QNN, which is the quantum algorithm for 10 qubit, and DNN is called deep neural net. That is, for us here is the classical neural net. And again, the quantum one is slightly better than the classical, but we cannot really declare triumph here. Next one. However, if we start running the same thing as a function of qubits, so we had the AUC for the TTH analysis, we run we plot the AUC as a function of qubit. We have been doing 10 qubit, but now we have a point and 15 qubits. And you can see from 10 qubit to 15 qubits, we just have 2 points, but it seemed to be, the AUC seemed to be better than the quantum results seem to be better than the classical one. So again, we are greedy. We want to say the QNN on simulator may have a quantum advantage over the classical deep neural net when the qubit is high from 10 to 15. So for 5 qubit, we don't see that. So you can see the blue line is on top, is above the yellow line. The yellow line is the classical curve, and the blue line is the quantum simulation. Okay, next one. So the work, we are excited about the quantum neural net these days. So we start doing more development with the Google simulator. So the work under this development is that in the official atlas analysis, TTH Higgs to gamma gamma, the LHC used 0.5 million events for training, validation, and testing. So we now should not limit ourselves to 100 events or even 3,200 events. On the Google simulator, we recently applied quantum neural net to TTH analysis using the Delphis data of 0.5 million event, which is similar to the sample size, the official atlas data analysis. Next. So here's the result using 500,000 events. And with QNN, the quantum neural net, we use 13 qubits, or DNN, we use 23 variables, the deep neural net, classical deep neural net. And we find the AUC are very similar. So this is only, we have this result only 2 days ago. So using the TTH analysis data, so 500,000 Delphis events and 13 qubit, QNN on the simulator now perform very similar to the classical DNN. However, the optimization of QNN is still under development. We hope we work harder, we will actually see the blue curve on above the yellow curve, and we can achieve quantum advantage with large data sets. So this is very exciting. Next. So now I go to my summary. We form an international and interdisciplinary collaboration with Department of Physics and Department of Computer Sciences of University of Wisconsin in Madison. We have collaborated with the CERN Quantum Technology Initiative from the IT division, and IBM Research Zurich and IBM TJ Watson Research Center. We have Fermilab Quantum Institute, Brookhaven National Lab Computational Science Initiative, State University of New York at Stony Brook, and also quantum computing and AI, artificial intelligence research of Amazon Web Services. Now, this is important. Although the era of efficient quantum computing may still be years away, we have made promising progress and obtained preliminary results in applying quantum machine learning to high energy physics. We are doing a proof of principle. Next. we have employed 3 different methods of quantum machine learning. Method 1, variational quantum classifier. Method 2, quantum support vector machine kernel method. These 2 methods were first proposed by IBM. Method 3 is quantum neural net. We have applied all 3 methods to 2 LHC, high energy flagship analysis, Higgs production in association with 2 top quarks, and Higgs to mu, using the Delphis simulation events. I hope one day my collaborator will allow me to use the real data. Okay, so now the next summary, the summary result from quantum simulator. With 100 event and 10 qubit, method 1 performs similarly to classical BDT and classical SVM. With 3,200 events with 10 qubits, method 2, the kernel method, on the IBM and Amazon quantum simulator may have a quantum advantage over classical classical machine learning method in the TTH channel. With 3,200 events and 10 qubits, the method 3 quantum neural net method on the Google quantum simulator may have a quantum advantage over the classical deep neural net in the TTH analysis. Concerning hardware, we have 3 experiments. The first one with 100 events, they are all with 100 events and 10 qubits. So for quantum SVM kernel and vector and the VQC method and the variational quantum classifier method. And so those are 10 qubits and the quantum neural network with 5 qubits. The IBM quantum hardware and the IBM quantum simulator show very comparable performance. Next. So here's a table of area under ROC curve. And what is interesting for you to see is the AUC from different methods. The first one is from VQC, the variational quantum classifier, is 0.83 for 100 events, but the kernel method for 3,200 events is 0.89, and also from IBM. And the kernel method from Amazon is also 0.89, is 3,200 events. And the QNN from Google with 3,200 events is 0.90. Now, what is interesting is that when we increase to 500,000 events with 13 qubit, we see the improvement on 0.93. You may see the AUC changed by not a lot, but in terms of sensitivity of physics analysis, it's very, very sensitive. So 0.93 is much better than 0.89 or 0.90. So the work under development is on Google Simulator. We recently applied the quantum neural net to TTH analysis using 500,000 events, which is similar to the sample size of the Atlas data analysis. So we obtained 0.93, both the quantum one and the deep neural net one. But we hope when we work harder, we will see the QNN will be better than DNN. Next. I'm almost done. Our results on both simulator and hardware demonstrate quantum machine learning on the gate model quantum computers have the ability to distinguish signal from background in a realistic physics data set and LHC data analysis. Now, the future development, we will investigate further, and hopefully we soon see the quantum machine learning outperform classical machine learning. And that's really our goal, in particular, when more qubits are utilized. Furthermore, the future quantum computer may offer speed ups in quantum machine learning, which could be very crucial to the high energy physics community, especially high luminosity LHC. Next. So the difficulty at this now is that only 100 events are used in hardware jobs. We are limited by access time. Only 10 qubits are used in the hardware job. So the circuit length and number of CNOT gates are limited. To use quantum computing hardware for machine learning in future high luminosity LHC analysis, we need to extend our study to larger number of event sample and more qubits. To demonstrate the future quantum computer offers speed up in quantum machine learning will be also a very important topic. Next. I have a prediction. I'm confident that in the near future, the quantum machine learning, QNN, quantum neural network method, can demonstrate in quantum simulation the quantum advantage with a large number of qubits. So when I say large, means more than 30 qubits. So I really hope that when we go beyond 10 qubits with a large number of events, we can actually see the quantum neural network will work better than the classical neural network. This, of course, in the context of application to higher physics, data analysis. And we are working hard on that. I think there's some hope. And I think to see quantum advantage is the most important goal in our study. Next one. I have used up a lot of the time, and but my Wisconsin members, Van, Gu, Sao Jinsen, Ray Chen, and Chen Zhu will be here to answer technical questions. Thank you very much.
So thank you so much, Saulan, for this wonderful talk. Thank you very much. It's a pity we cannot applaud in person. And thank you for reporting all these very interesting results. So we have quite a few questions online. Yes. I also wanted to introduce the co-organizers of our seminar, Andres Ambainis from Latvia, João Seixas from Lisbon, who will today moderate the questions, and Simone Montangero from Padova, Italy. And so, João, please go ahead. Maybe we could agree on a period of 10-15 minutes for the question session, so that we have a goal in terms of time, not to extend the session too much, but I leave it to you to manage. Please go ahead, João.
I think it will be difficult because there are a lot of questions. So let's see. The first one is relatively easy. Vladimir Korepin is just asking the name of the collaborators in the Xianyang Institute. but I think when the presentation will be ready and available, I think
it's on my page 1.
Yeah, it's in page 1. So that's okay. You put it already. Thank you.
Yeah, the page 1 is Xu Chen Wai. He's a professor in computing.
Thank you. So Sanmai Ganguly asked if instead of directly classifying the event, did you try tagging the final state object using a variation quantum classifier and check if you gain in performance?
Chen, you want to answer that?
So could you mind repeat this question again? Sorry.
So instead of directly classifying the event, did you try tagging the final state object using VQC and check if you gain in performance?
Right. So we have not done so far. I think this talk is mainly just directly classify the events, which is also done in the Atlas and CMS analysis a lot. So, but what you say might be interesting to look at object level. Yeah, so I think so far we are focusing on the event level to only investigate the various quantum algorithms.
Thank you. So by the same person, without per object tagging scale factor, can a reliable systematics be computed using this method?
I don't think we're that advanced.
Yeah, this is a really tough question, I would say, yes. So from the Deep Learning Partnership, supervised or unsupervised learning? I think this is an easy one also. So the question is whether it's supervised or unsupervised learning.
It's a supervised learning.
Yeah, sure. Crazy Maisie asks whether did you find the difference between the prediction classification on the simulator and the actual quantum hardware?
Well, I have shown various comparison of Chen. Yeah, you can see this is a variational quantum classifier in the TTH and the H2 mu. The red curve is hardware, the blue curve is simulation. So my conclusion at the bottom of the page, they are very similar. But I don't think we have that kind of accuracy yet because this is only from 100 events and we only run once with the hardware. And I have to stress, make you know that getting access to hardware is non-trivial because they are very expensive.
Yeah. There is another question which is reasonable, whether there is any reason for the choice of this loss function. Okay, for a classification problem, something like binary cross entropy would be more canonical.
Yes, before we have tried the cross entropy method. However, for our analysis, the classification is the first step. After that, we have another step to measure the probability, to measure the probability of the interesting events. For our case, the interesting events are events with a high classification probability. For example, if one event is classified as a signal with probability 0.6 or 60%, it's not interesting for us because the uncertainty is too high. So if the event is classified as a signal with a probability more than 90%, the event will be interesting for us. Because of this requirement, we found that the MSE method, the mean square error method, is better for us.
Okay, thank you. So now a question by Pedram Bagassa. So did you check that there isn't any overtraining That is, did you check for the performance of the final classifier in train and test data?
Yeah, when you can answer. The answer is yes, we did check, but
yes, we did check. In the slide, we showed that we have 3 different data sets, 1 training data set for the training and 1 validation data set for evaluation, and there's a lot of test data set. We use the 3 different data sets to avoid overtraining. The final performance is produced on the test data set.
Okay. Thank you. Yet another question by Pedram Bargasa. So for both methods, could you please show the final variable of a signal background classification that is the equivalent of a machine learning output?
I don't think we have that prepared.
Yeah. Okay.
But we can do it privately.
Mm-hmm. Thank you. So yet another question from Chris Amazy. The difference between quantum and classical AUC is minimal. So considering the number of samples in your data set, do you observe a difference in accuracy at all?
For our case, the accuracy is similar, but AUC is very important for us. Just before, or just like in the presentation, Solange said, the AUC improvement from 0.9 to 0.93 will have a huge improvement on the final significance.
Thank you.
We actually found to look at the accuracy is not that informative, but the AUC is much more sensitive.
Okay, thank you. So from Alessandro Farazze, how long did you take to compute the quantum kernel on a data set with 3,200 events?
Sargent, you know how, you can answer that.
Yeah, if you are asking for 10 qubits, it's less than 1 hour.
Mm-hmm.
Are you talking about simulation or hardware, actually?
Simulation, I think.
Simulation, okay.
Yeah.
Thank you. So for Michael McGugan, I don't know whether this is the name. Can you generalize to Higgs to gluon? What are the complications?
You mean you want to find the bump of the Higgs mass in the gluon?
Yeah, well.
That would be really difficult.
Yes.
The peak would be all over the place.
Yes. So from Sanmai Ganguly, should be highly suppressed by QCD background.
Well, we do have a pre-selection of the events. So a lot of junk have been reduced before we actually use the input. The same as when we do our classical analysis.
Okay, thank you. So yet another question from Crazy Mazy. Could you also quantitatively compare training effort for QNN versus DNN?
So Jun or Van, you want to answer that?
Okay, we can compare the training performance, for example, the AUC, but we usually don't take the training AUC.
Okay, thank you. Another question from Pedram Bargasa. Are the results published? If so, he would like to have the references.
We are making a very fast progress. And the publication is extremely slow. So by the time we get a journal to look at us, we're already in another steps. So I don't know how to keep up with that.
Mm-hmm. Thank you. So there is one question, but apparently there has been an answer in the talk. But then anyway, let me ask the question anyway. So in method 1, rock curves, the two cases show an opposite behavior in recognition of signal and background. Can we think to improve the classification by fusing data with features regarding detectors?
I didn't understand.
You mean combine the data set from TTH and from H to mu? That's
using basically the features, detector features, just to check whether it gets better. I don't know how this could be done, but anyway, maybe you know.
Well, I think right now, as I said, for each analysis, we have a pre-selection, both working with quantum or classical. There's some trivial procedure, like for you have 2 muon, and if you work on TTH, you don't look at the 2 muon final states. So you don't really need such a sophisticated tool to separate them.
Thank you. So there is just a final comment. There is some confusion out there between the significance of the AUC versus accuracy. The AUC indeed quantifies the quality of a classifier much better than accuracy. However, for the application, the accuracy is what counts. Well, okay.
Well, it depends who's, who decide on what works and what doesn't work.
Mm-hmm.
I mean, for us, in the Atlas analysis, is the AUC, which is sensitive to our final accuracy, our final result, sensitivity results. And when we work with I know that computer scientists like to use accuracy, but we find accuracy doesn't do a lot for us.
Thank you. So there are no more questions. Thank you.
Okay, thank you very much, João, and thank you very much for all the questions. So I would ask Chen if you could stop sharing the screen. I just want to announce the next seminar. So let me get the slide here. So thanks everybody for attending our QuantApp seminar, and thanks in particular to Shaolan Wu for her wonderful talk and for sharing these results, and her team for sharing these results with us. So to conclude, I just wanted to announce our next session. On the 2nd of December, we will have Ignacio Sirac from the Max Planck Institute of Quantum Optics talking about solving quantum lattice gauge theories with quantum computers. And finally, I would like to thank our co-organizers, Andres Ambainis from Latvia, João Seixas from Lisbon, and Simone Montangero from Italy. And last but not least, the team behind the Zoom and YouTube working so fine, Sagar Pratapsi and Diogo Cruz. So thank you very much, everybody, and special thanks to Shaolan for this talk, and see you next month. Thanks and bye-bye.
Bye.
Thank you.
Thank you.
Bye.
Thank you. Bye-bye.